So in today's video, we're going to be looking at 10.1 and 10.2. 10.1 is basically what we've already done and just discussing that a little bit more in depth. But 10.2 is where we really get into where we're heading for the rest of the semester. It's not the easiest chapter in the world, and it is a fairly long chapter, so bear with me as we go through this. But I will do plenty of examples and plenty of homework problems so that you can see how this works. So first of all, I want to go through 10.1. 10.1 looks at using a specific value, so just one value, in order to estimate what the population mean is. So a point estimator is a single point that estimates a population parameter. Okay, the population parameter that we tend to look at through these two sections is the population mean. Okay, so we want a way that we can estimate the population mean by using a single point. Now, we've done this before. We've used the sample mean. We've taken a sample of our population and then we have used the mean of that sample to estimate the mean of the population. That uses a single point, a single value, that sample mean, to estimate the population mean. So a point estimator could be using the sample mean, x bar, to estimate the population mean. And we call the population mean mu. Okay, so I can use the sample mean as a single point that will estimate the population mean. The other way that you can do this, which is what we're going to discuss in 10.2, is where you actually have an interval estimator. An interval estimator gives an upper and lower boundary of an interval that should contain the population parameter. Okay, so what an interval estimator does is it will give you an interval. It will give you an upper and lower bound of an interval that we hope will contain that population parameter. So we could have an interval that we hope would contain the population mean. So we could say, let's say that you have an interval, I don't know, between 5 and 10. So 5 is your lower bound, 10 is your upper bound. And you would hope from the information that you've got, you would hope that your population mean would land in that interval. Okay. That's what we're going to be doing in 10.2, and that is a very long chapter. But what I want to talk about right now is using a point estimator. And as I've said, we've done this a lot before, so I won't talk about this for too long. The problem that we have a lot of the time is that you won't actually know what the population mean is. If you don't know what the population mean is, then it's very, very difficult to figure out how accurate your estimate is. Now, if we know what the population mean is, that makes it way easier to figure out how good an estimate you have. So something that we use is called the mean square error, and we've kind of looked at similar things before. The mean squared error for a point estimator, let's say the sample mean for some sample in the population, would just be the estimated value of the difference between the sample mean and the population mean squared. So we are looking at the error between your point estimator and the population parameter that it is estimating, so in this case, the difference between the sample mean and the population mean, and we are squaring it to make it a positive distance. So all the mean squared error does is it looks at how much of an error that you have distance-wise. Now, if you had a perfect estimator, which basically never happens, you would get a mean squared error of 0. Okay, because your sample mean would equal your population mean. That means your point estimator equals the thing it's estimating. It's a perfect estimator. That never happens. So you basically never get a mean squared error of 0. But what you would like is to make this thing as small as possible. Now, it turns out that as long as you've got a representative sample, the sample mean is the best estimate that you can have for the population mean. Okay. Other ways that you could estimate the population mean could be by taking the median of a sample. You could do the mode. So the best thing that you can do is to use this sample mean to estimate your population mean. It is the best point estimator that exists. So that's the first thing, is you want to make sure that the mean squared error, or the MSE, is as small as possible. Okay, so that mean squared error is the smallest that it can be when we use the sample mean to estimate the population mean. The other thing that you have to be aware of, and this is the case with sample means, you have to make sure that it is unbiased. What that means is when we take the means of the sample means, or if we were to take, let's say, the mean of all of the sample medians, we should end up with the population parameter that we are trying to estimate. Okay, so you need to make sure it is unbiased, which would mean in our case that the mean of the sample means equals the thing that you are trying to estimate, that population mean. So we have to make sure for it to be unbiased that the mean of the point estimators from each of the samples is equal to the population parameter that you are estimating. So the mean of the sample mean should be the population mean. You would need that the mean of the sample medians would give you the population mean, etc. So we know that this is the case for the sample means. We've looked at this before. So we already know that that is the case. We know that the sample means are unbiased. So, as we've said, the sample mean will give us the best estimate that we can have for the population mean. This isn't always the case with some of these things, some of the population parameters that you can estimate. One of those where it isn't a great estimate is when you are trying to estimate the population range. Using a sample and taking its range to estimate the population range normally isn't a very good estimator. So the sample range is not a good estimator for the population range. Okay. Reason being, let's say that your population range was this. So A was the smallest value in the sample, or in the population, sorry, and B was the largest value in the population. So you have a range here of B minus A. So your population range is B minus A. Now, you're going to have all of your population data points all along this line. But even if you were to take a representative sample, so you took them all the way along, let's say you took those, okay? your sample range is still smaller than your population range. You can never get it large enough unless you took the two endpoints. You're never really going to get it large enough that it's going to equal or be very close to that population range. So the sample range is not a good estimator for the population range, just because the range isn't like a centralized value. The range just gives you largest minus smallest, and whatever sample you took, it could be representative, but the largest value in the sample minus the smallest value in the sample will always be smaller than the population range unless it includes the two endpoints. So just because you have a representative sample in this case, it may not necessarily give you a great estimate for the range anyway. So keep that in mind when you do this. But most of the stuff that we're going to be dealing with is means. So we're going to be looking at the population mean and looking at a point value that can estimate that population mean, or looking at an interval that will contain that population mean. So now in 10.2, we're going to look at an interval estimator for the population mean. So all we do for an interval estimator is we want to find some upper and lower bound on an interval such that we would like the population mean to be contained within that interval. So we would like to find just two values, some lower and upper bound, such that our population mean is contained within that interval. Now, the smaller the interval you have, the better the estimator it is. Because you could say for some problem that you could have a lower bound of 0 and an upper bound of 1,000,000. Well, that's great, but where would that mean lie within that interval? There's way more of a variation in there. So what we really want is a smaller, more compact interval where we are more certain that the mean is within that smaller interval, because it will give us a better estimator. So it may be more difficult to find, but it will give us a better estimation for where that mean actually lies. To do this, we are going to go back to the central limit theorem. Now, we know that if we have a sample of size greater than 30, then the sample means have an approximate normal distribution. So if the sample size is greater than 30, then we know that the sample means have a normal distribution, or an approximate normal distribution, I should say. And they have a mean of the population mean, because the mean of the sample means is the population mean, and our standard deviation is the standard deviation of the data points divided by the square root of the sample size. So again, I am looking at the distribution of the sample means. So this mean is the mean of my sample means, and this standard deviation is the standard deviation of my sample means. And I know that it has an approximate normal distribution as long as my sample sizes are at least 30. Now, we have said before, if we go back to the empirical rule, if you remember that we want roughly 68% of the data lies within one standard deviation of the mean, roughly 95% lies within two standard deviations, and 99.7% lies within three standard deviations. So let's draw ourselves a quick normal distribution again, a normal distribution curve. Okay. So your mean is in the middle, and we know that roughly, let's say we go two standard deviations either side of the mean. So I'm going to call that standard deviations of my sample means. Okay, it doesn't matter whether it's a standard deviation, just a normal standard deviation, or whether it's a standard deviation of something else. This thing has normal distribution. We know our sample means have normal distribution. So we're going to use that as our standard deviation, because this is the normal distribution curve of the sample means. So my standard deviation is the standard deviation of the sample means. So we know that within 2 standard deviations of the mean, I should have roughly 95% of my data in there. I will tell you now that it's actually 95 point something % of the data lies within 2 standard deviations on a normal distribution curve. It isn't exact. To get exactly 95% of the data to lie in some interval from the mean, you actually have that it's 1.96 times the standard deviation. So this was an estimate, but the actual value, I will tell you now, is 1.96 times the standard deviation. So for what we do normally, just saying it's roughly 2 standard deviations is good enough. But just for argument's sake right now, and just so that you can see what's going on, I want to keep it as exact as possible. So if I want exactly 95% of my data to lie in some interval, it is actually within 1.96 times the standard deviation away from the mean. So if that is the case, I know, going back to when we did z values, so remember, z-scores for a z distribution, you have a mean of 0 and a standard deviation of 1. If you have a mean of 0 and a standard deviation of 1, that would mean that the probability that you lie between negative 1.96, so if this is 0 and my standard deviation is 1, this value here would be negative 1.96, and this value here with a mean of 0 and standard deviation of 1 would be 1.96. So between negative 1.96 and 1.96, the probability that I lie in that interval is 0.95. I have a 95% chance, exactly a 95% chance of lying in that range. Now, we're going to use a z transformation here, but I'm going to use the z transformation of my sample means. So if I do that, I know that z is x minus the mean divided by the standard deviation over the square root of n. Okay, this thing here is just the standard deviation of my sample means. This is my mean of my sample means, which is just the population mean. Okay, so all I have done is replaced z with what we're using with the sample mean. Sorry, that should be a sample mean there. So I've got a sample mean minus the population mean over sigma over the square root of n. Okay, so I've just done our z transformation with the sample means. So now I'm going to rearrange this formula. So what I'm effectively going to do is multiply up by sigma over the square root of n. So I'm going to multiply through by sigma over the square root of n. And then what I'm going to do is I'm going to subtract my sample mean all the way through. And then what I have to do, because I have a negative of the population mean, I'm going to have to multiply through by -1 or divide through by -1. What that does is it actually flips these inequalities around. Okay, if you would like to do this, you can, or you can take my word for it. But what you should get within this probability is this formula. Okay. As I said, if you have any issues with that, let me know. But you can work that through. So now what you can see is that there is a probability of 0.95. There is a 95% chance that my population mean lies between this value and this value. So I have a 95% chance that the population mean will fall in this interval. So for some given sample mean and a population standard deviation, we have a 95% chance that the population mean will lie in this interval. Okay. We actually call that 95% that we use. So we know that the probability that the mean lies between these two values is 0.95. So we've got a 95% chance that it lies between the two values. We call that 95% a confidence, okay? It's how confident we are that the population mean will lie in that range. Because that is how confident we are, we call this thing here, this interval, we call this a confidence interval. And in this case, with confidence of 95%. Okay, because we are 95% confident that our population mean will lie in that interval. Okay, what that basically means, because we're 95% confident that our population mean will lie in that interval, okay, what that basically means is that 95% of my samples should give me a sample mean where this interval will contain my population mean. Okay, we can have as many samples as we want within our population, but 95% of the samples that I have should give me a sample mean such that my population mean will lie in this interval. So I'll write that out. 95% of the samples in the population, so you can take samples of whatever size n that you have, 95% of the samples in the population will give a sample mean x bar, so you'll get multiple x bars depending on what sample you pick. Each one will have its own sample mean, but 95% of them will give you a value for x bar such that the population mean will lie in the above interval. Okay. Now, depending on how confident you want to be that your population mean is contained in this interval, depends on what your interval is going to be. Okay, you tend to find the more confident that you are, okay, the more confident that you want to be that that population mean is contained in this, the larger the interval is going to be, okay? Because the smaller that this interval gets, it's great because you will have more of an idea of what the population mean actually is. Because if you say compared to between 0 and 1,000,000, okay, population mean, like you have no idea where it lies in that range. But if you said, well, I've got an interval of 50 to 55, that gives you a much more accurate representation of what that population mean could be. So the less confident that you want to be, the smaller the interval it will give, but it will give you more of an idea of where that population mean should lie. But you're just not going to be as confident that that population mean is contained in that interval. Okay, so the more confident that you want to be that this interval contains the population mean, the larger this interval will be. Okay. So the way that we actually write this is slightly weird, but bear with me and then I will go through some examples and some homework problems of how you can work this. First thing that you have to be aware of is that if sigma is known, that means that my population standard deviation is known, okay? You're going to get problems sometimes where the population standard deviation is known, where they will give it to you in the problem, which is great because you can use this, but sometimes they do not give you the population standard deviation. You have no idea what it is. So in that case, you actually have to use a different equation to do this, but we'll talk about that later on. But if you are given the population standard deviation and either your sample sizes are greater than 30 or the population that you start out with is normally distributed. So you can have one or the other. As long as one of those things is true, then you can go ahead and use this, okay? So you need the population standard deviation to be known. And then you either need to take sample sizes of greater than 30, which means that we therefore know, if you look back at your notes, that therefore means that we know that these sample means are normally distributed. Or you need that the population itself is normally distributed to start with, because therefore any sample that you take from it must also be normally distributed. Therefore your sample means are normally distributed. So you need one of those two things as well as your population standard deviation being known. Then this is where it gets slightly weird, but bear with me and you will see how this works out. Some percentage, and we'll talk about what this value actually means in a minute, some percentage confidence interval. So for example, we just did a 95% confidence interval where we were 95% confident that our population mean was in that interval. So some percentage confidence interval for the population mean is, and here is the formula, and it comes from what we just did. And again, bear with me on the notation, we will talk about it. Okay. So this would give you an interval, if you want to write it in interval notation. It would look like that. Okay, so all you have here is your upper and lower bounds. It's just written slightly differently. Okay, let's talk about this and what this alpha is that we've introduced here. So let's say, I'm going to give you an example that will show where we're going with this and what this actually means. Let's say that we wanted a 95% confidence interval. So, for example, we wanted a 95% confidence interval. Okay. For a 95% confidence interval, to make this thing 95%, that would be 100 multiplied by 0.95. Okay. So this value here, there is an easier way to do this, so bear with me, but I'll show you what it's actually trying to tell you. This thing here would be 0.95. Okay. So 1 minus alpha would be 0.95. That must mean that alpha is 0.05. What this z here is, so z alpha over 2, that's just a notation for a particular z value. All that is a z value such that we have our confidence interval, in this case 0.95, we're 95% confident. We want that confidence level, that area, to land in the middle of positive z and negative z. So let me show you on a diagram what that would look like. That z of alpha over 2, okay, again, it's a z value. It's in standard normal distribution, that z value, okay. What we've then done is use that z value to then use it within a formula where you have your sample means and your sample standard deviations. But we are just looking for a z value, so take it way back to basics where we looked at z values. You have a mean of 0 in the middle, okay? Z of alpha over 2, okay, remember that this thing is symmetric, okay? If I want a 95% confidence interval, I'm going to put 0.95 of my area in the middle. That z of alpha over 2 is this value here, okay? Negative z of alpha over 2, because this thing is symmetric, lies symmetric right on the other side of 0. And I have 95% of my area, 0.95, that lies between those two values. Now we know from our previous example that this is actually 1.96 and this is negative 1.96, okay? Because we said that roughly within 2 standard deviations of the mean, you have 95% of your data. The actual values are 1.96, so within 1.96 standard deviations of the mean, you have 95% of your data. So I made it slightly more accurate in this case. But that z of alpha over 2 is literally this value here. Now, let's say we didn't know that it was 1.96. So let's get rid of that for a second. Okay. If I get rid of that, and let's say we wanted to know what this value was. Okay. Remember, when we try to find a z value, a z-score, we always use inverse norm on the calculator. So whenever we try to find a z-score, we use the inverse norm. It will ask you for an area, a mean, and a standard deviation. And the area that it asks for is always the area to the left of the value that you are looking for. Now, in this case, because they're always going to be symmetric, you're always going to get positive z of alpha over 2 is here, negative z of alpha over 2 is here. Okay? So that means, let's do this example here. I'm going to have, if I've got 0.95 of my data lies here, okay, I'm going to have 0.05 of my data lies here and here. But it's split in half. So each one of these areas here and here has an area of 0.025. Okay. So what I can do, okay, let's say I'm looking for this value here. Okay. You plug in the entire area that's to the left of that value, which in this case is 0.975. Your mean is 0, standard deviation is 1. That would give you z of alpha over 2. The other way that you could do it, if you're trying to find z of alpha over 2, just plug in this 0.025, a mean of 0, standard deviation of 1. That would give you negative z of alpha over 2. And then if you were looking for z of alpha over 2, just get rid of that negative. Okay, so you could just get rid of that because it's symmetric, so it doesn't matter. But either way, this is how you would find that z of alpha over 2 value. Okay, if you were doing it, let's say they were doing an 80% confidence interval and they wanted to find z of alpha over 2. For an 80% confidence interval, okay, between two values, z of alpha over 2 and negative z of alpha over 2, you've got a mean of 0 and a standard deviation of 1. I want an 80% confidence interval, so my area here is 0.08. That means that my area between here and here is 0.2. Therefore, the area of each one is 0.1. because this thing is symmetric, okay? So if I was trying to find z of alpha over 2, I could do inverse norm of, you could do either one. I could do, to find this one, my area to the left is 0.9 because it's 0.8 plus 0.1, mean of 0, standard deviation of 1. Or what you could do either way, because you only need one of these values because they're just positive and negative of one another, you could type in 0.1 as your area, and that would give you negative z of alpha over 2. And if you just wanted z of alpha over 2, get rid of the negative. Okay? But these two are just positive and negatives of one another. Okay, so that is all that was saying. Let's come back to our theorem here. So if you are trying to find this confidence interval, okay, you will be given a sample mean. You will be given a population standard deviation, and you will be given a sample size so you can find the square root of n. The only thing that you would have to find is this value here, z of alpha over 2, okay, which we've just discussed. And all you do is type it into the calculator under inverse norm. So now let's take a look at this example. So they have given us a random sample of 100 car engines which have a mean weight of 425 pounds. Construct these different confidence intervals, so we have to do one for 80%, one for 90%, 95% and a 99% confidence interval for the population mean if the standard deviation of the population is 900. So they've given us the sample size, they've given us the sample mean, and they've given us the population standard deviation. So we have to construct 4 different confidence intervals. One where we're 80% confident that it will contain that population mean. One where you're 90% confident that it will contain the population mean. One where you're 95% confident, and one where you're 99% confident. So if you remember our formula, okay, for our intervals, it's x bar minus this z value that we need to find out, multiplied by the standard deviation of the population over the square root of the sample size. And then you're going to do the same, but this time you're going to add them, and that will give you your upper bound. So this is your lower bound, this is your upper bound, okay? So they have told us, if we look at this example, they have told us that our sample mean is 425, okay? We still need to figure out that z value. Our population standard deviation is 900, and then our sample size was 100, okay? Okay, so for each one of our samples, for each one of our confidence intervals, we have to figure out this z value, okay? So let's do that first for the 80% confidence interval. So if we were 80% confident that this interval would contain that population mean, for 80% confidence between negative z of alpha over 2 and z of alpha over 2, we want 80% of our data, 0.8. That means between here and here, I have 20% of my data, 0.2. So on each one of those areas, I have 0.1. So to figure out z of alpha over 2, I'll do this for negative z of alpha over 2 because it's easier to see. I'm going to do inverse norm of the area to the left of negative z of alpha over 2, which is 0.1. My mean is 0 because I'm looking at z values. I'm in standard normal distribution, and my standard deviation is 1. So if you go into your calculator and do that, you should get roughly negative 1.28. Okay. If you want z of alpha over 2, that would mean z of alpha over 2, because remember, this is negative z of alpha over 2 that I've looked at here. So z of alpha over 2 would just be 1.28. Okay. So I can then go in and plug this in as 1.28 and 1.28. Okay. And then I can just plug it in, and that will give me my interval. So if you look at what they've done here, for our 80% confidence interval, when you multiply 1.28 by 900 over the square root of 100 is 10. And then you're going to add it to 425 and subtract it from 425. And you'll get 309.8 and 540.2 as your interval. Okay. You can do this for a 90% confidence interval. I'll show you this one quickly to get the z values. For a 90% confidence interval, between negative z of alpha over 2 and z of alpha over 2 with a mean of 0, standard deviation of 1, you want 90% of the data to lie between those two values. That means the area on the outside, then if I divide that by 2, I'm going to get 0.05. So the area here is 0.05 and the area here is 0.05. So I can figure out this value very easily if I do inverse norm of 0.0501, And if you plug that into the calculator, as you'll see here, it would give you negative 1.645. So we can take z of alpha over 2 as 1.645. And then you can just plug that in. Okay. You can do the same for the 95% confidence interval and the 99% confidence interval, and you can figure those out. However, there is an easier way of doing this, and that involves using a calculator. So if you go to your calculator and you click on the button that says Stat, okay, it should be below the delete button. Click on Stat and go over to where it says Tests. So you'll have to double click the right arrow to get over to Tests. Number 7 on your calculator says Z interval. Click on Z interval. Okay. Now, the first thing it will ask you is whether you're inputting data or if you're inputting statistics. Okay. We're inputting statistics. We have been given a sample mean. We've been given a population standard deviation. We don't have a list of data. Okay. If you ever had a list of data, it's very unusual that they would do that for you on a Z interval, but if they do that for you on a confidence interval, you would be inputting data into a list and then your input would be data. But right now they've given us summary statistics that we can use. So your input is statistics. Then the population standard deviation in this case is going to be, what did they say? It was 900. So your population standard deviation is 900. Your mean for the sample was 425. The number of things in the sample was 100. And then you can do this for each confidence interval. So the first confidence level that we have is 80%. So you put that in as 0.8, okay? For a 90% confidence interval, you'd put in 0.9. For 95, you put in 0.95, etc. Okay, so always put it in as a decimal, not as a percentage. Then you click calculate. And the values that you should get, you may be slightly off by a rounding error from what they have in this example, because they have rounded that 1.28, for example, for the Z score on the 80% confidence interval, that has been rounded to 2 decimal places. What they do on your calculator is that they keep it as a full value the whole way through. So you may be slightly off due to rounding errors. But what you should see is an interval. They will give you the interval and then they will give you the sample mean and the number of things in the sample which you already put in. But it will give you that Z interval. It will do all of this for you. All you have to do is input that. So remember, you went to Stat, Tests, and Z interval. You type in the information and it will give it to you. Okay. Let's look at another example. This one came off of the homework. And it says a research company desires to know the mean consumption of milk per week among males over age 31. A sample of 2597, so that is the number of things in your sample, so your sample size is 2597. Males over age 31 were drawn and the mean milk consumption in that sample was 2.1 litres, okay? So 2.1 is the mean of the sample. Assume the population standard deviation is known to be 1.3 litres. So you've been given your population standard deviation sigma. Construct the 95% confidence interval for the mean consumption of milk among males over age 31. Okay, you can do this either on a calculator or by hand. It's up to you. Just when you do this, bear in mind there may be a rounding issue, so you may want to do it on your calculator, but I want you to know where it comes from, okay? This is what your calculator is doing. It's taking your sample mean, it's figuring out what that Z value is. So for a 95% confidence interval, which we did back here somewhere, if I can find it, for a 95% confidence interval, it is doing this calculation here and figuring out what that Z of alpha over 2 is, whether it be negative or positive, but it's then giving you the positive value. You always take the positive Z value when you plug it in, and then you're going to add and subtract it from that sample mean. But always take the positive value. So they have figured all of this out and then plugged it into our formula here, and they've got the population standard deviation, they've got a sample size. So let's try this again with the calculator. So you're going to go to Stat, Tests, and go down to number 7, which is Z interval. Okay. Again, you've been given summary statistics. They've done all of this for you. So input is statistics. Then sigma, which is your population standard deviation, is 1.3. Your mean that you've been given was 2.1. And then N, the number of things in the sample is the number of males, which is 2597. And the confidence level that the confidence that you want to have that this interval will contain your population mean is 0.95. And you go ahead and calculate. And in my calculator, I have been given the interval of, if I can find a blank page, my interval was 2.05 and 2.15. Okay, so I am 95% confident that the mean of the whole population lies between 2.05 and 2.15 based on what I have been given from my sample data and my population standard deviation. This is the interval that I have figured out, and I am 95% confident that this interval contains the population mean. So problems like this, they bring up a term called the margin of error. And all that is, if we go back to our formula that we had, the margin of error for any interval is just this part here. It's the z value, that z of alpha over 2, multiplied by the standard deviation over the square root of n. So this part here on each one, you're just adding or subtracting the margin of error from the sample mean. Okay, so whenever they give you a margin of error problem, all they are doing is that they are giving you this whole value here. Okay, so they have worked out a z value, a sigma, and the square root of n. So this says the mean amount of money spent on lunch per week for a sample of 90 students is $16. If the margin of error for the population mean with a 98% confidence interval is 2.3, construct a 98% confidence interval. So when we do this, you have been given that margin of error, and you have been given the mean for the sample. So you've got the sample mean and you have this margin of error term. So for our problem, we have been given a mean of $16 and this margin of error for that 98% confidence interval of 2.3. So if I take my sample mean of $16 and I add and subtract that margin of error from that value, I should get a 98% confidence interval. They have already figured out that z value for a 98% confidence interval. They have some population standard deviation that they have used, and we know that n was 90. So they have used some information that they have not given us or that they have worked out and have not shown us, so we don't have to do it. They've done all of that for us and just told us what that term was for a 98% confidence interval. So in our case, all we have to do, with that being our margin of error and $16 being our sample mean, all we have to do in this case is say that our, I think it was 2.3, yeah, 2.3 was our margin of error, is we add and subtract it from that sample mean. So we can be 98% confident that this interval will contain the population mean for that problem. Okay, just don't overcomplicate the problems where they give you the margin of error. You don't have to figure out any z value. You don't have to go looking for a population standard deviation. They won't give you one a lot of the time in these problems. They will have done all of that for you, and they will just give you that term that you can add and subtract if they give you a margin of error. Okay. This type of problem, I'm going to show you two ways of doing it. For some of you, right at the end, before we had to leave for spring break, when everything was going kind of crazy on campus, on class on that Monday, I put a program in on some people's calculators that was called sample size. So for those of you that have that program, you can use it here. For those of you that don't, there is on Blackboard, if you go onto the Blackboard page and you have a cable for your calculator, you are able to download it. For those of you where I just didn't have the time to get it onto your calculators, or if you weren't in class. So that sample size program is on the Blackboard page. So if you want to go and get that, you can, and you can download it using the cable that came with your calculator. However, for those of you where neither of those options are possible, I'm going to show you how to do this problem from scratch. So in these problems, what they are asking for is the sample size. So they will give you some information and you will have to figure out what the sample size is where they have given you a specific level of confidence. So in this case, they've actually given you a variance rather than a standard deviation for that population, but that doesn't matter. All you have to do is square root that. So they have said that assume that the variance is 3.61. If you square root that, you get the standard deviation for the population. And he thinks the mean is going to be 7 toys per year. What is the minimum sample size required to ensure that the estimate has an error of at most 0.12 at the 85% level of confidence? Okay, I'm going to show you the long way to do this for those of you that cannot get to the program on the calculator, but it's really simple once you know what you're doing. I've just told you about that error term. Okay, our margin of error term is equal to that z-score multiplied by the standard deviation over the square root of the sample size. What I want to do is rearrange this formula for n. So if I do that, I'm going to multiply both sides through by the square root of n. That's going to get it off of this denominator here, and it's going to make sure I've got no fractions. So I would get the square root of n multiplied by the error term is equal to that z value times the standard deviation. Okay. Now I'll divide both sides through by the error, which will give me this if I divide both sides through by the error. And then if I square both sides, I've solved for n. Okay, so that will give me my minimum sample size that is required where I have a z value for a particular confidence level. So in our case, for our problem, we have been given that sigma, our standard deviation, would be the square root of 3.61. The mean, so our sample mean is 7. Doesn't really matter in this case, we won't use that. Then it says, what is the sample size required to ensure that the estimate has an error of at most 0.12? So my error, that E term, is 0.12. And I know I have an 85% level of confidence. So let's come back to my formula here. I know that this sigma here is the square root of 3.61, okay? It's my standard deviation, it's the square root of the variance. E, our error term that we wanted, was 0.12. I don't want to have an error of more than that. Then I need this z value, okay? In this problem, we want to have an 85% level of confidence. So for my z of alpha over 2 in this case, okay, negative z of alpha over 2 would be here, and z of alpha over 2 is here, and 0 is in the middle. Remember the z value, it's in standard normal. I am just looking for that value. I want an 85% level of confidence. So my area here is 0.85 between the two values, okay? And this is just positive and negative of some value. So I know that the area outside here and here must be 0.15. So the area in each one of those would be 0.075. So that means that I have an area of 0.075 here and an area of 0.075 here. So if I want to find z of alpha over 2, I'm actually going to go for an easier option and just find the negative version of it, and then I can make it positive. So I'm going to do inverse norm of the area to the left of that value, which is 0.075. I'm in the standard normal here. I'm looking at z values, mean of 0, standard deviation of 1. If I do that, I get negative 1.44 basically. So that is negative z of alpha over 2. So z alpha over 2 is just 1.44. Okay, so now going back to the problem, I know that my z alpha over 2 is 1.44. I know that sigma is the square root of 3.61. And then I'm going to divide that by 0.12 and then square that value. And I get 519.84. We always round up in these cases. So my sample size is 520. For those of you that do have that sample size app on your calculator, if you go to program, you should be able to scroll down to sample size, okay? Again, if you do not have this, there is the program on the Blackboard page that you can download if you have the cable. If not, you'll have to do this the long way. It's not that long, but just be aware that there is a program that will do this for you. If you go to program and sample size and click enter, option 1 says x bar with sigma x. This is that you know the sample mean and the population standard deviation, which in our cases we do, okay? Then we're going to go to MOE eval, okay? It will ask you for the standard deviation, it will ask you for the error, and it will ask you for the confidence level. And it will calculate all of this for you. Okay, and it will do exactly what we've done before, where we figured out our sample size, but it does it all for you. Okay, so just be aware that is there. It will shortcut this and do that calculation for you. As I've said, you can do it the long way. It isn't that long. It's just that you have to do it by hand. But you should get the same answer in both ways. And this thing will automatically round up for you. Okay, so keep that in mind if you can download that program from the Blackboard page or if you already have it on your calculator. Okay, this distribution is very, very similar to the normal distribution. If you were to look at t distribution, it's almost like a flattened version of the normal distribution. But it doesn't depend on the mean and the standard deviation like our normal distribution does. It actually depends on something called the degrees of freedom. The more degrees of freedom that you have, the more that this thing becomes like a normal distribution. So it becomes closer and closer and closer to a normal distribution the more degrees of freedom you have. So what are degrees of freedom? It's basically the number of data points in your sample that you can change and still get the same sample mean. Okay, so if you think about it, let's take 1, 2, 3, 4, 5 as our data points in our sample, let's say. If I take the mean of these, so if I add them together, I'm going to get 15. Divide by the number of them that there are, there's 5, and I get 3, okay? Now, I can change these data points to be whatever I like, okay? But I want to keep this same sample mean. So let's say I change these to be, I don't know, -1, 1, 2, 6, and 8, let's say. Okay. So I now have these data points. However, you will notice when you add these all up, I now get 16, but I still have 5 data points. So I'm going to get a different sample mean. However, if I were to change this last data point here and instead set it to 7, my sum of these values is still going to be 15, and I am going to end up with the same sample mean. So what I've learned from this is I can change 4 of these values to anything that I like, but I have to keep the last value at something strict in order for this thing to still have the same sample mean. So I can change 4 out of 5 of my values to be whatever I like and still end up with the same sample mean, as long as I fix that last value to be something that will keep the sample mean where it's at. Okay. So in this case, the number of degrees of freedom is the number of data points that I can change, and that is 4. So the degrees of freedom is always, degrees of freedom, we denote it df, it's always the sample size minus 1, because I can change n minus 1 of these data points as long as I put that last data point to be whatever it needs to be to keep the sample mean the same. So my degrees of freedom is n minus 1. The more degrees of freedom you have, hence the larger sample size that you have, the more that this thing will look like a normal distribution curve. But they act in very much the same way for the purpose of what we're looking at. Why do we use this? Well, if you look back at the examples that we've done with the z distribution, okay, when we've looked at z intervals, we were given the population standard deviation in all of those problems. That's great. However, if you think about it, the reason that we are looking at these intervals is because we want to find an interval that might contain that population mean, so we can have an idea of what that population mean might be. Well, if we don't know what the population mean is, we're hardly going to know what the population standard deviation is. But we've used that population standard deviation in our z-interval calculations to calculate what this interval might be. But if we don't know the population mean, 99% of the time you're not going to know your population standard deviation. That's where this t distribution comes into play. Okay, so I'm going to use this t distribution where instead of using my population standard deviation, it's going to use the sample standard deviation just as an estimate for it, because we will most likely not know the population standard deviation, as we don't know our population mean in a lot of real world cases. So now I want to look at how can we create a t interval. Okay, so when we don't know that population standard deviation, we can't create a z interval, but what we are going to create is a t interval. So when the population standard deviation sigma is unknown, so we don't know our population standard deviation, and again, the sample size n is greater than 30, or the population is normally distributed. So you can have either one. Either one of these will make those sample means normally distributed. Then I'm going to create this confidence interval again, and it's going to have some weird notation just like last time. But it's going to act in very much the same way. If I want this confidence interval, so I'm some level of confidence, some percent of confidence, that confidence interval for the population mean, so I want to be however confident that the population mean will lie within this interval. Okay, it looks very similar to what we've had before. There's just a couple of small things. We're still starting out with our sample mean, okay? And then we're going to add or subtract to give us our lower and upper bound. So your lower bound would be this value, and your upper bound of the interval would be this value, okay? S is your sample standard deviation. So we don't have a population standard deviation, but we will be given a sample set of data, so data from a sample, and we can figure out its standard deviation. So we've got a sample standard deviation here. N is again the number of things in that sample. So we're still doing a standard deviation divided by the square root of n. We're just now using our sample standard deviation instead of our population standard deviation. Then we have this t value here. It's exactly the same idea as when we used z values the last time, okay? And your calculator will do it for you. You just have to figure out the area and the degrees of freedom. So again, if you are trying to find a t value, let's draw this out. Again, it looks very much like a normal distribution, okay? Let's take some t value that we want here. And again, this thing is going to be symmetric, okay? The area that you want, again, is the area that is to the left of the value that you are looking for. So you can look for positive or negative of that t value. It makes no difference. Okay, I tend to go for the negative t value just because trying to figure out that area is much easier. So depending on your confidence interval, let's say we've got a 0.8 level of confidence, so 80% confidence interval. So we've got 0.8 will be here, and we would have 0.1 on either side. So to figure out this value here, if you go into second and distribution on your calculator, so where you find inverse norm, so second distribution, then scroll down. Underneath inverse norm is something called inverse t. Click on that. What this is going to do is allow you to find these t values. So the area that we want, again, is the area that is to the left of that value. So in this case, we would have inverse t. The area to the left of a value that I'm looking for is 0.1. By all means, you could use 0.9, which is the area to the left of this value. You would just get the positive version here and the negative version here. You can just get rid of the negative at the end. It makes no difference. So I'm going to use 0.1 as my area. Then it will say df. That is the degrees of freedom. The degrees of freedom is n minus 1. So whatever your sample size is, minus 1 goes in as your degrees of freedom. If you figure that out, it will give you a t value. If you get a negative value, you've worked out this value. If you get a positive value, you've worked out this value, okay? You want the positive version. So if you want to work out this one, that's fine. Just remember to make it positive afterwards, okay? So that is how you figure out that t value. But again, when you do these problems, there is a way simpler way of doing this. If you go into your calculator, go into stat and go to tests, right underneath where we've looked at z interval, there is a t interval. If you click on that, again, it will give you the same type of thing as before. It will ask you if you are looking at a list of data or if you are looking at statistics. It will ask you for the sample mean, the sample standard deviation. Remember, we use a sample standard deviation now instead of a population standard deviation. It will ask you for the sample size and the confidence level, and it will figure out this interval for you. Okay, it will figure out that t value for you. So for this problem, it has said that a survey of several 11 to 12-year-olds recorded the following amounts spent on a trip to the mall. So they have given you a list of data here. They haven't given you summary statistics. They've given you a list of data. So you would have to put that list into a list in your calculator. Okay, so put that data list in. And then it says construct the 80% confidence interval for the average amount spent by 11 to 12-year-olds on a trip to the mall. So what it wants is it wants a confidence interval such that we are 80% confident that this interval will contain the population mean. So it will give us the mean value of what all 11 to 12-year-olds spend at the mall. At the moment, we only have a sample of them. But this confidence interval that we get, we should be 80% confident that all 11 and 12-year-olds spend roughly this amount at the mall. Okay? So if you put that data list into your calculator, okay, and then you are going to, once you've done that, it's going to calculate all of the sample mean, the sample standard deviation from your list. You then scroll down, okay, on T interval, put the list in, the frequency should be 1, and the confidence level is whatever it gives you. So in this case, you would put in 0.8. It should then give you back some interval, okay? Now, my interval that I got was 21.80 and 29.18, okay? So that was the interval that I got. But as I said, if you need the actual T value, if you need to go the long way and calculate it using this, you can, because we now know how to get those T values. Or you can do it the shorter way and just use the T interval program on your calculator, and you can go ahead and use that. Okay. If you have any questions whatsoever, just let me know and I will be happy to help. I know that this isn't the easiest chapter, so please just jump onto office hours and I will be more than happy to help with any questions you have. But hopefully we've covered most of the types of questions that you're going to get in your homework. I'll see you in the next video.